stop me. All right, so what if I have a PDE and I want to do a series solution for that? That's the Cauchy-Kovalevsky theorem. It has a lot in it. So if I have the initial condition, it all depends on the initial condition, and they talk about that a lot in the book, that the initial condition has to be nice, and it has to match up. And I thought that actually his geometrical arguments in the book were very beautiful on the initial condition, that you can't have an initial condition not match up. They have to splice together when they come together. If there's some kind of sharp, you're attaching them together, it's not going to work out right. So that initial condition has to have a certain form. In this case, the initial condition has to be analytic in the neighborhood of the origin. And we also need that the initial condition and all of its derivatives at the origin have to be analytic. Then the initial value problem, which we refer to as the Cauchy problem, has a solution which is defined and analytic in that neighborhood of the origin. And the solution is going to be unique in the class of analytic solutions. That's a mouthful. They mention here in the class of analytic solutions, you've never heard anything like that before, because either they say it's unique or not unique. So in the past, you shouldn't have heard any class of solutions. But the odd thing about PDEs is that if you make the space that you're working on bigger, you can find more solutions in that space. So if you restrict down, say, I only want analytic solutions, in that case, I will have a unique solution. There might be other solutions to this equation that are not analytic, but if I restrict just to that set of analytic solutions, I'm only going to get one. So this is an example I took from the book. And I gave you some homework problems, and it's very similar. And I hope you'll look at this chapter and think, oh, this is actually getting more calm, and everything seems to be much more organized. So in this problem, you have ut is equal to ux, and you're given an initial condition. The first step is to check that the initial condition satisfies the condition of the Cauchy-Kovalevsky theorem. So is that analytic? Yes, it is. So we're fine. And then you need to check that the right-hand side is analytic at 0, because that's where the initial condition is centered around. And indeed, it is. So both of those two conditions are verified, so this Cauchy-Kovalevsky theorem holds. So if I'm going to plug and chug and actually derive the solution, I can't actually do it as easily as I did for the y prime equals y. I have to find all the derivatives at 0, the partial derivatives, because I think you guys did this in advanced calculus where you had to expand in multi-dimensions a Taylor series. I think you might have even done it in Calc 3. Does that sound familiar? So in the series solutions for Taylor, so you can look it up. It's a formula, and you get, it's a much messier looking formula because you have not just the partial derivatives of x, but you have the partial derivatives of y, and you have the mixed partials in there too. So sound familiar? All right, I have part of this. I have at least the order 2 terms, so you can see them here. But the formulas are, it's popping things into that formula. So here I have u of 0x. I take the partial of that with respect to x, and I take the partial of that with respect to x, and I take the third partial with respect to x, and eventually get to 0. They wanted up to 3rd order. I think I got lazy and I did up to 2nd order. But then you plug in 0 into all these guys, and you get u at 0, 0 is 1. These are going to be the coefficients inside your multi-dimensional Taylor series. Then you need all the derivatives with respect to t as well. So you need ut, utt, all at 0, 0. And the way you get them is from the equation itself. So ut is given to you by the equation. You already know what u at 0 x is. You know, so you plop those things in. Ut at 0, 0 is u at 0, 0, ux at 0, 0, which turns out to be 1 times 0, which is 0. The mixed partial utx, if you calculate it, you get u times ux by using product rule, ux times ux. and then you plug in 0, 0, and you'll get 1 times 2 plus 0, which is 2. So in this way, you can go through and calculate every single one of them. UTT turns out to be 2, and then you can just do all the rest. I mean, this is not, is it clear how I'm getting these? I'm just going up to this one, and then taking the derivative with respect to t. So I'll get first times the derivative second, which gives me the mixed partial here. Then second times the derivative first, which gives me the mixed partial here. So right here I'm using product rule from this guy to get this expression. And then I put in 0 inside these. In the previous, I already got utx is equal to 2. Since everything's analytic, uxt is also equal to 2. If you remember from Calc 3, the mixed partials are equal if the function's continuous. If the mixed partials are continuous. Oh yeah, he had that in there? Good. So then you take the Taylor series for 2 variables around 0, 0, and it looks like I gave you up to order 2. So order 3 is going to be even more messy. It's got more, it looks kind of like the Pascal's triangle. That's what you're going to get. And so you put it in and put in all the coefficients, plug in all those coefficients, and you're going to get u of xt is equal to 1/2 times 2x squared. I didn't reduce it in any way. So this is not really useful because you probably won't find a pattern. Even for this simple equation, it's probably going to be difficult to keep, because the third order terms are really scary, and the fourth order terms, forget about it. So there's probably no hope of finding a pattern. But what you could do is this gives you a partial solution or an approximate solution. So if you wanted to get some idea of what your solutions look like, this is the way to do it. And we can plot that, and that's what it looks like if you plot that solution in 3 dimensions.
This is more of a numerical scheme.
It's
I feel like we're just working off the initial conditions and you just keep counting out to find the equation.
right. I would say it's an old school way of getting the numerical solution, right? Because if you talk to any of these guys that worked in this, like if you talk to Ames, they didn't go to the computer because it was such a pain to go to the computer. Edward Lorenz told me that what he did to get his Lorenz butterfly, he literally had to do the punch card thing with the Fortran, and then he had to turn in those punch cards, and someone had to, there's a piles of code sitting there, so someone has to pick up his punch cards and then run the code, and then he has to plot those points that come out of the punch card by hand. So those graphs that are in his paper are by hand. They were done, I think, in the 1950s. So it was long enough ago that it was not simple. And so it would be easier for him to just run a series solution than it would be to go through that. And in fact, I talked to another guy. He actually has the first dynamic model for weight change, and he worked at IBM, and he eventually wrote a book where he simulated the model for all different cases. It's just a simple model, and he simulated for all, and he just put it in tables, and then there were a lot of table books. Ames shelves were filled with books of tables. Those are all gone. If you go to anybody's office here, nobody has a book of tables. You know, like the integral tables in the back of the Calc 2 book? There were books on solutions to all kinds of differential equations. It was called Handbook of Differential Equations. And they would just have like solution to the Riccati equation, solution to this equation. It was all in this one book. So those books are obsolete. So as a numerical method, I don't think so. I think this one you can just put the equation itself right on Maple or MATLAB and tell it to solve it, and it'll probably give you a closed form solution or a pretty decent solution. I think it's only used for what I just told you earlier, to derive other equations. Say it again?